welcome back. So in this lecture, we will talk about some big O expressions, right? We won't jump into the space complexity directly because in previous lecture we have understood like how we can calculate the big O or like time complexity of an algorithm or of a function, right? So in this lecture, let's take a break from it and let's try to understand a little bit more about the big O expressions. Okay, so what we have to do, we have to consider few points to understand how big O works, right? How we use big O notations. So first thing you have to keep in mind, like we only talk about the uh, general trends, right? We talk about only the big pictures, okay? We don't go into the exact detail. So let's say I took a function, okay? It is running, it have two parallel for loops, okay? So let's take an example of this one. Okay, so in the previous lecture you have seen like the big O notation of this one was coming like somewhere like 4 of n, right? Big O of 4n, right? Ideally it should be big O of 5n because this plus plus we can consider as plus equals to, but let's keep it simple. Let's keep it as 1 n number of times, right? Right. So yeah, so it had like n operations here. This will be running as n operations n number of times. This will be running n number of times. This will be running n number of times, and then this will be running n number of times. So we have calculated, we have four operations which will be running n number of times. Okay, so whatever the value of n is, like it will run that much number of times. Okay, these operations will be calculated that much number of times. So what we do, we don't care about like how many operations are being used, how many numbers of times, right? If we have 4n, then we simplify it down to n because we only care about the big picture. Okay, so let's say we have two parallel for loops. If these two loops are running parallelly, right, and both are running for the n number of times, let's say 1000 times, let's say the value of n is 1000. Okay, let's say it is 1000. Okay, so both the loops will be running 1000 number of times, right? So what we say, like the time complexity of this is O of n, big O of n. Okay, we don't care like how many parallel loops are running. Okay, we only talk about the big picture, so we will use big O of n, like it is going to run for the n number of times. Okay, so yeah, this was one thing, and I'm getting few errors here from line number 41. Okay, so it is because of this. Let's comment it. Okay, so let's get back to our example. Yeah, so as I have said, like constant doesn't matter. Okay, so we have this example. Let's say we have 4 O of n running in one code in a function, which as we have seen few seconds back, right? So we simplify it down to big O of n. Okay, like this. So if we have 300, big O of 300, what does this mean? So it simply means like whatever the value of n is, be it 1000, be it millions. Okay, so loop will have only 300 operations no matter what the value of n is. Okay, so if it is going to have 300 operations only, then why can't we keep it like constant, right? So big O of 1. Okay, instead of writing big O of 300, like a code is having 300 operations which are constant, which are not going to increase or decrease, doesn't matter what the value of n is, so we can keep it like big O of n. Okay, so in simple words, the broad trends which we have to care about. Okay, so what about this one? Right now this is like 18n square, right? So this n cap 2, it basically means 18 n is 18n square. I don't have to write it. Why I'm writing it, I don't know. Okay, so what should be the simplified version of this expression? Okay, so as I said, like we remove the constants, we don't care about the constants, so we will simply remove this 18 from here. And what we will do, we will simply write big O of n square, because we know like there are 18 loops which are running in quadratic fashion. Okay, So why we have to consider all those 18 when they are going to run for the same time? Okay, so we will care about the n square. We remove the constants from it. Okay, so this is how we basically ignore the constants and we worry about the general trends, right? And the second thing, like, you have to consider is the smaller terms doesn't matter when you are working with the big O expressions. Okay, and what I mean by smaller terms, as you can see, I have few expressions here. Okay, so this one have like big O of n plus 10. So that means there are some n operations. Along with that, we have some 10 constant operations, right? So does this constant operations matter when we have n number of operations? So the answer is no, right? So we can simplify it down to big O of n, okay? Because these things will just confuse us, right? Just give me a second. Okay, yeah. So we simplify it down to big O of n. Okay, so now in this one we have big O of 200n and 10. So same we have to do, I think you got it by now, like we have to, how we'll simplify it. So we have to remove the constants first, like this one we will remove, and then we have to remove this one. Okay, so what does this mean? Like we have 200 operations, like 200 uh, places where the n number of times or operations are being used. Along with that, there are 10 constant operations which are being used. Okay, so we simplified it down. We have removed the constants from it, and we just worry about the broad trend or the big picture, right? Because end of the day, it is going to run for the n number of times, right? So why we bother considering the constants and the exact number of loops and everything? Okay, so we just worry about the broad trends. Okay, so here we have big O of 3n square plus 200n plus 20. So what should be the simplified version of this big O expression? Any guesses, guys? Well, as I've already mentioned, the smaller terms doesn't matter. So if you think, like, if you pass 100 in it, okay, so let me write it down actually. Then you will understand a little bit better. Okay, if you pass 100 in it, let's say, let me put it in bracket. Okay, so 100 square, that will become 100 into 100, right? So this thing will become 100 into 100, right? And multiplied by 3. So I think this will be 10,000. 10,000 multiplied by 3, it will be 30,000 something, right? And then on the other hand, we have 200 to 100 multiplied by n, which whose value we have passed like 100. Okay, and then we have passed 20. Okay, so now it will become this one and this one. Okay, so we have 30,000 here and plus 20,000. I think I wrote it right. Plus 20. Okay, so the maximum number of times the loop is going to run is this 30,000, right? So the maximum number of time, this is what we are going to get, right? So why bother ourselves caring about these values, these smaller values? Okay, so that is why we will simply ignore these values. Okay, and we will just focus on these ones. Okay, so how we can simplify it down? We can simply write big O of n square, right? So where is a cap? Okay, n square. So we can simplify it down like this. We removed the constant and then we have removed all the small numbers out of it. Okay, we simplified it down to this expression because end of the day it is going to run for the quadratic time only, right? Its runtime will be quadratic only, right? So why we bother ourselves caring about these small values in it? Okay, so here's a takeaway: we don't worry about the constants, we don't worry about the smaller terms when we are writing the big O expression. Okay, so now some important considerations when you are working with the big O expressions. Okay, so arithmetic operations are always constant. What I mean by that, so if you multiply 2 with 2, you will get the result in same time the way you multiply 10 million with 10 million. Okay, so if you multiply the larger number with the larger number, you will get it within fraction of seconds, right? And in same amount of time you will get the result when you multiply it with the smaller number. Okay, so you will get the result in constant time, short and simple. Okay, so doesn't matter what is the value of n, you are going to get the result in the exact same time. So that is why arithmetic operations are always constant. Okay, be it multiply, addition, division, or whatever it is. Okay, so now variable assignments are also constant. Why variable assignments are also constant? So let's say you have created a variable, let's say y. Okay, you have assigned some value to it. You have assigned, let's say, 2000. Okay, and then you have reassigned it some value, let's say 5000. So it doesn't matter what is the size of the value. Okay, it is going to assign it in the same amount of time only. Okay, so that is why we say like variable assignments are also constant in it. Okay, so now in the third point, as you can see, like accessing elements in an array by its index or value of an object by its key is constant. So if you are trying to access an element in an array, okay, but by its index, so it doesn't matter if it is a thousandth element, if it is a second element, or it is a 10th element. If you are accessing it by its index, then it is going to give you the result in the exact same time when you're trying to access the thousand element. Okay, right. So um, let's move to the fourth point here. In this one, like we have seen an example already of this one. Okay, so in a loop, the complexity is the length of the loop. Okay, multiplied by whatever logic you have written in the loop. So in the loop, we have already seen like if the value of n is 100, then the loop is going to run for the 100 iterations. Okay, and if the value is 3, then the loop is going to run for the 3 times, right? But let's say you have added another loop inside the for loop. Okay, inside the loop. So let's take this example. So here in this for loop, if we have added this loop, okay, so the time complexity will become O of n square, right? We have seen already in previous lecture, right? So this loop's time complexity will get multiplied by this loop's time complexity. Okay, so that is why I mentioned like in a loop the time complexity of the is the length of the loop. Okay, basically the size of the loop multiplied by whatever logic you have written in the loop. Okay, so this is all about the, we can say, expressions in big O. So let's see few more examples to understand the big O notation a little bit better. Okay, so let me just write a for loop quickly. Let I equals to 1, and then I smaller than equals to math dot max. Let's say I want to run it for 3, and then I'll pass some number, let's say n. Okay, lg, let's just try to log the value here of I. Okay, or we don't need string, let's log it directly like this. Okay, and here we have to use I plus plus, obviously, and let's wrap it in a function. Okay, let's say print max loop, because the name doesn't matter here, it's just for the sake of example, right? So let's move it in here, and then let's pass the value as n, and yeah, let's use this function here itself. Okay, so here what do you think will happen, like if I try to pass something like 2? Okay, so as you can see, it took the maximum number. 3 was bigger than 2, so it took 3, right? So that is why our loop ran for 3 times, 3 iterations we can say. Now let's try to loop it for 5 times. So 5 is the 5, we have passed the value 5, like we have passed the value of n as 5. So 5 is bigger than 3, right? Because max will pick the maximum number out of these two, right? So 5 is bigger than this 3, so mat.max will pick 5, right? So the expected thing is it will return 5 iterations, 1 2 3 4 5. Okay, so what do you think the time complexity of this function will be, guys? Can you take a guess? So the time complexity of this one is going to be big O of n, right? Because the n is directly affecting the iterations of the loop. Okay, let me write it down. So minimum it is going to run, it will loop for 3 iterations, right? But why it's working this way? But max it can run to infinity, right? Infinite loops, right? Because the number can be as larger as infinity, right? So this loop will run for infinite iterations maximum, right? So that is why the big O notation for this one is going to be big O of n. Okay, like this. So let me write a similar function. I just want you guys to take another guess, like what will happen in this one. So print, let's name it as min loop. Okay, here I'll change it from max to min. Okay, and then let's see what happens. So here I'm calling this function and I'll pass some value, let's say 4. Okay, so it is running for just 3 iterations. Okay, let's pass a smaller number, let's say 2. So it is running for 2 iterations because 2 was smaller than 3. So this method took 2 as a number. Okay, now let's try to print 10. Okay, so now this specifies, like, it doesn't matter whatever value you pass for the n, until or unless it is smaller than 3, it is not going to run. Okay, it is going to pick 3 only for iterations. So maximum iterations this code is going to have is 3. So normally the big O notation for this one should be big O of 3, right? Because it is going to run for the 3 iterations maximum, right? And we can simplify it down to big O of 1, because we have a constant and we simplify the constant numbers to 1, right? Because we talk about just the big picture. Okay, so I hope you guys got a better idea now, like how the big O expressions work and how we write the big O expressions. Okay, and how we simplify it down basically, because this much detail will just confuse you guys, right? So that is why we just pick the broad trends. Okay, and I have actually picked a chart. It's a nice chart which I found on Medium, which I can show you quickly. It represents like all the big O like time complexity related things. So here we are passing, so this line will basically represent the size of the input which you pass. Okay, and this one will represent the runtime which your code took, or the time which your code took to run. Okay, so here let's say you have passed a larger number. Okay, and constant is O of n. So O of n means it is, this line is like parallel to this input size n line, right? So that means this one is the fastest one because it is not taking much time. It doesn't matter like what is the size of n here, it is just taking constant time here. Okay, So this is considered as a good one. And then we have this line which is taking a little bit more time than the size of input. Let's say you have passed the value of n as 10. Okay, so it will take 2 or 3 minutes, 2 or 3 seconds, we can say, just for the sake of example. Okay, so it will take a like little bit of runtime to execute the result. Okay, and then we have this linear line, which means it will be same as the size of input. Let's say you have passed 1000, then it will take same amount of time to execute the code, okay, to give you the result, right? And then these are the little bit bad ones, we can say. Like, we haven't talked about all these, so you just ignore them for now. But you will have an idea, like where where we have to see, like, if we have a constant time, then what we have to consider it, like how we have to categorize it, is it a good or bad, right? So this way we can easily categorize our code's performance. Okay, so if it is O of n factorial, that means it is simply like 10 times more than the size of the input. Let's say you have passed 10, then the time it took is like 2 seconds, 3 seconds, like 10x the input size. Okay, so this way it will be exponential, and this one will be quadratic, n cube. Okay, so these are all the ones which we are going to learn, like in the future lectures in this series, so you don't have to worry about these ones. We have already seen O of 1, O of n, and O of n square. Okay, so we will see these ones as well, but in the future lectures. Okay, so yeah, this is it for this lecture, guys. So in next lecture, let's finally learn about the space complexity. Okay, so till then, happy coding.